Good afternoon, everyone, and welcome to today's lecture of your deep learning course. Padmavati ma'am, I have given you the right so that we can start with the lecture for today.
Okay. Thank you.
Thank you, ma'am.
Hello. Am I audible?
Yes, ma'am, audible.
Okay, thanks. Good afternoon, everyone. So today's session is on feed-forward neural network, right? So let us start. Let us try to understand what we mean by feed-forward neural network and what are the key terms used in this network. Right? Feed-forward neural network is a neural network which are connected with each other. And in specifically, I can say neural networks are densely connected, right? So in this, what we do have is we do have set of we do have set of layers, and in each layer we do have n number of neurons, right? And each neuron is connected with every other neuron of the next layer. Okay, and as well it applies to the previous layer. As I explained, each neuron in the layer is fully connected to every neuron in the next layer. We do have three different kinds of layers. Let us try to understand what are those. The first one is input layer. The next layer is called as hidden layer. And third layer is output layer. Correct? So here we do have input layer. In input layer, as the name itself suggests, we need to feed inputs, okay, these samples in this particular layer, and this particular layer is fixed to 1. That means we will have one input layer in our feed forward neural network. As a case of input layer, it applies to output layer as well. That means output layer also number of layers in the output layer are only 1. Correct? Whereas in hidden layer, we do have flexibility. We can have one hidden layer or we can have multiple hidden layers. Let us try to let's move further. Each layer computes some output. Okay. And every layer takes input from the previous layer. Specifically here, every layer means each neuron of every layer, okay, takes input from the previous layer. That particular, what we are saying that the previous layers are responsible, or neurons of previous layer are responsible to pass on the output to the next neuron, next layer of neurons, right? So here we mean that every neuron in each layer computes some equation, fine, and based on that particular equation we do have definitely that particular equation, it what it actually has is it has the data plus it need to have some parameters, right? So based on that data and parameters, each neuron will compute some functionality. It applies some function on the input data and the parameter, okay, and later on it will produce some output. Okay, so in brief, each neuron will compute some function, and that particular function takes the input x as input, plus as we need to analyze the performance of the model, so we need to tweak every time, we need to tweak the weights, right? So that f will accept data as well as my weights, right? So it will accept x, that is sample, and the weights will be given to the function, and the function, what it will do is it computes the some equation, and what it will do is I will show you what type of equation it will be solved. Okay, it will solve the equation and it will produce the output. That particular output will be moved to next, or it will be passed to the next neuron in the hidden layer. Okay, similarly, output of the last hidden layer will be passed as an input to the output layer. Fine. Let us try to understand this architecture. Whatever I have described with respect to feed-forward neural network, I have represented the in the form of architecture. Okay, so here we do have input layer. Input layer is this. Okay, where I'm feeding three different data items: x1, x2, and x3. Okay, as we discussed, input layer will always be only one. Number of input layer will always be only one. That is this particular vector x1, x2, and x3. In a similar way, we do have three different output layers. Okay, y1, y2, and y3. Fine. So now in this particular case, you can say this, let us consider this particular neuron of the hidden layer. These two are two hidden layers. The one which are represented with blue color, they are representing the hidden layers. The layer which has been represented with yellow has been is representing output layer, whereas this particular the first layer over here, it is representing the input layer, right? Now let us try to understand this. Okay, let us take the first neuron. What this particular first neuron is accepting as an input. Let us try to understand that. It is accepting all three data items of the first sample, plus it will also taking the weight values, that are parameter values. Okay, the arrows here are indicating the parameter value which are assigned with the help of w1. Okay, and plus it will also accept this particular bias. Okay, so this particular neuron, okay, it will compute the output based on x1, w1, and b1. Okay, now here you all must try to understand, here x1 is fixed. Okay, to get any output of this particular neuron, x1 over here is fixed. We cannot change the attribute values or data items of x1. But what I can change, suppose my output, whatever output is something that we don't have so many neurons, we do have only single neuron, and we are getting some input, that is x1, and we are taking w1 as weight matrix, and we are taking bias term as we are taking b1 as bias term. Okay, so in that case, what this particular neuron will compute, it will compute y hat equals to some function of w1 into x1 plus b1. Okay, so in that case, what it will generate some function, some output based on that particular function. Suppose consider that function is giving us the linear output. Okay, so in that case, what it will generate the output as W1 into X1 plus B1. Okay. So here B1, the bias term is always added to increase the flexibility of the model so that my data is fitted over the fitted properly, right? For that sake, what we are doing is we are trying to add different bias terms in the neural network. Fine. So now try to understand, we do have single input, that is X1. We do have single weight W1, and we do have single B1. Okay, for this particular neuron. This particular neuron is accepting X1, W1 and B1. So what it will compute is, it will simply compute X1 into W1 plus bias value will be added to this particular multiplication, X1 cross W1. So it generates some output. Okay, so whatever output it has generated, if I consider that function is following linear function and it generates some y hat, if that y hat is further away from the actual y, so what happens if it is further away from the actual y? We have seen that it should be again what the loss will be high, because as it is showing the big difference between y hat and y, actual y and predicted y. So there is a huge loss. Whenever there is a huge loss, we all know that what we need to do, we need to come up with some sort of optimizer. So that optimizer, what it will do is, it will try to change or update values of weights and biases in such a way that when we compute on this particular X1, when we compute next time the same function, when we apply the same function, that is W1 and B1, now this time my y hat should be closer to y as compared to the previous step. Okay, this is what we discussed in the previous case. Whenever there is a huge loss, okay, what we need to do is, we need to again retrain the model after updating the parameters. Okay, now you must very well understand, whenever we do this sort of whenever this particular neuron is producing some y hat with some W1 and B1 values, some random values, then whatever y hat that it is generating, what it should do is, it should compare with the previous values. Okay, that is predicted value will be compared with the actual value, and later on what it should do is, it should update the parameters W1 and B1 accordingly. It should update in such a way that next time whenever you perform on this particular data set, data item, the y hat should be closer, or it should reduce the loss as compared to the previous loss. Fine. With that particular consideration, let us try to move ahead with this particular architecture. In this architecture, what
Excuse me, ma'am.
Yes.
Ma'am, what is bias?
Bias, what are we trying to do is, we are trying to add some sort of like flexibility should be added to the model to fit the data properly. Okay, so you all know that we used to write down some sort of linear equation, right? In that particular linear equation, we used to solve that y is equals to mx plus b. Okay, so that b term was the intercept over there, right? It is similar as that term. Okay,
Yes, ma'am.
we will discuss about in detail about the activation function. In activation function, actually it generates some sort of output. Okay, so the mathematically, if we see the graph after generating the activation function, okay, that is after generating the output, then my bias is the role of the bias is to shift my intercept values from left to right. Okay, So in the last class or in the last session, we have discussed that weights and we need to or our algorithm will learn the weights during training period. Okay, so this it learns the weight in the sense it updates the weights in such a way that the loss of current step should be less than the previous step. So instead of only updating W weights, we also need to update the bias terms. Okay. So updating weight and bias term both include in the training period. In order to reduce the loss, we will also update weights as well as we also update the bias terms. Okay. Fine. Now let us move ahead and let us discuss the architecture. In this particular architecture, what we have taken like you can see, this is representing the first hidden layer. This is representing the second hidden layer, right? In the first hidden layer, we do have used 4 neurons. Okay. Similarly, in the second hidden layer, we have used 4 neurons. Fine. So obviously, in the previous example, I asked you to imagine only one neuron exists, and for that particular neuron, it computes some functionality f, and that f will be given the input as x1, w1 and b1. So that f will be computed f of w1 into x1 plus b. Correct. So later on, what it will do is it will I also informed that functionality f is it can represent a linear function or it can represent a non-linear function. Most of the cases that function is non-linear function. Okay, there are various non-linear functions which are also known as activation functions. Okay, we will discuss in detail about activation function later on. But you try to understand that every neuron is able to solve that particular equation. Okay, that means it need to compute the function. Here also it computes some function. Here also it will compute the function. Here also. So every neuron is capable enough to produce some intermediate result. Getting it? So that particular whatever result that this neuron is generating, that will be passed to the neurons of the next hidden layers. See, the output has been passed to this neuron, the output will be passed to this, the output, whatever output it has generated, it will be passed to each and every neuron of the next layer. And you can also see one more thing, that each input layer, all 3 inputs are connected with every neuron of the first hidden layer. Similarly, each neuron of first hidden layer have connected with every other neuron of the second hidden layer. Similarly, all neurons which are specified in this particular second hidden layers are connected with all neurons of the output layer. Okay. For that sake only, I have defined, while defining feed-forward neural network definition, I have defined with the term as dense, because these networks are highly densely connected with each other. Okay. With this, let us try to understand what that particular functionality is about, what that F is about. F is nothing but functionality which is applied on each of the neuron of these hidden layers as well as this particular output layer. The same functionality can be applied on this particular output layer as well. Okay, so each neuron will take the function f, will compute some function f, and that particular f will, as I explained, it takes w, x and b as an input to compute some output. Correct? So how it computes? It computes based on this particular equation. So wi into xi plus b, based on this, that is aggregation of W and Xi will be added with some bias terms. Fine. So you can see here, I have already explained, but you can also see the equation. This particular equation is linear equation. Okay. Whereas this particular F, mostly it is non-linear equation. So for that sake, F we call it here as a non-linear function. Fine. And we do have in neural network, we do have different kinds of non-linear functions such as linear, logistic, ReLU, and tanh. All these are different activation functions which are used over here, right? Which can be used over here. Any one can be used. Again, depending on the scenarios, we need to choose. For some scenarios, we need to choose linear. Some other scenarios, we need to choose logistic and so on. Okay. We will see in detail about each of the activation function, and after seeing the functionality of each activation function, it will be very much clear to us that which of these should be used in which particular scenario. Okay, for that sake, we need to understand the functionalities of these functions. Fine. So we will discuss this in tomorrow's session about the activation function, details of the activation function. But today's class or session, we will dedicate it to architecture, understanding complete architecture of feed-forward neural network. Okay, so let us try to understand how this particular linear function can be computed. Okay, for simplicity, I have taken two neurons at input layer, one hidden layer, two neurons with one hidden layer, and two neurons at the output layer. Correct? Now, let us try to understand how can I compute this particular equation for this simplest architecture. Okay, so as you can see here, this can be let us try to write down the what W here, W1. This is representing W1. Okay, this particular matrix is representing W1. Okay, here we need to have 2 cross 2. Okay, we need to also understand dimensionality. Before that, let us try to understand the dimensionality, then only it will be clear when to use which particular or weight matrices. Here x1, x1, x2. Here we do have inputs as x1 and x2, correct? So in this particular input layer, if I asked you to compute or let me know the dimensionality of input x. Yes, one of you unmute and let me know the dimensionality of input layer.
Cross 1.
2 cross 1. Fine. Definitely, it is a single vector which is representing my input, but it has 2 attributes, so it should be 2 cross 1. Correct. And what is the what about the dimension of this particular W1?
2 cross 2.
2 cross 2.
You are not audible clearly.
2 cross 2 because it is taking 2 inputs and there are two neurons, so it will be 2 cross 2.
Yes, very much correct. So weight matrix W1's dimension is 2 cross 2, correct? And what about dimension of the first bias term?
2 cross 1.
It should be 2 cross
1.
Yeah, it should be 2 cross 1, correct? Now, let us try to understand the dimensionality. How do I need to represent using this particular linear function? Okay, it shows, as you all answered it correctly, weight matrix, that is W1's dimension is 2 cross 2. X1 and X2 are representing vector, input vector. So again, it is 2 cross 1. Whereas this bias term is, one term is passed, one term of the bias will be passed to first neuron of the first hidden layer, and only one hidden layer, right? So one term will be passed to first neuron of the hidden layer, and second term will be passed to second hidden layer, second neuron of the hidden layer, right? So B11 is passed to this, and B12 is passed to this particular neuron, correct? So in this simple matrix, this is a simple matrix multiplication, matrix into vector, 2 cross 2 into, you simply compute this 2 cross 1, so it comes out to be 2 cross 1. Again, this we can do again, there is a linear function we need to apply. So it comes out to be W11 into X1 plus W12 into X2 plus this bias term will be added, B11. Similarly, this W21 into X plus W22 into X2 plus B12. So this is the resultant of the linear function. Okay, this term is resultant of the linear function. On top of this, whenever we add the functionality, that is, whenever we try to apply non-linear function on top of this particular linear value, whatever it has generated, so it will generate some sort of result. Okay, so that particular values will be again forwarded to next neurons. Here in this, it will be directly forwarded to our neurons of the output layer. But if we introduce some more hidden layers, so the output of this neuron will be passed to intermediate neurons, the hidden layers. Okay. Any doubt till this? Okay, if in case of no doubts, we can move ahead. Just go through this. So what you need to map is, you need to map the number of parameters with the parameters and layers. Here, the first column is indicating number of parameters, total number of parameters which are required. Here, parameters, we know only two types. One is weight, the other one is bias. Layers, we know there are total number of layers. Let me go back and tell you. Total number of layers are L layers. Okay, this and this one. This is the input layer, and in this L minus 1 is representing what? In this L minus 1 is representing the number of hidden layers. If you add plus 1, so it becomes L layers. Okay, so here L minus 1 layers are representing of hidden layer, and this one is representing the output layer. So try to compute the total mapping of this. Because understanding of dimensionality in feed forward neural network or any other type of neural network is very important. Once we understand the dimensionality, it will become very easier for the next sessions.
Ma'am, I have a query.
Query I will take at the end. So let us complete. Is the query related with this function, this question?
Yes, ma'am. Previous one actually.
Okay.
Why are we representing the equation in form of matrix?
Because okay, because this is vector, input layer is vector, because you need to understand to answer that question. So let me explain. This is an vector, input layer is vector. Again, hidden layer we do have an vector, but as I said, every neuron is connected with every other neuron. Okay, every neuron is connected with every other neuron of the first hidden layer or any other layer. If we take any two layers, every neuron of first layer is connected with every neuron of the second layer. Fine. So whenever we are forming the connection, okay. So here x1, what is the weight of this particular x1? That is represented by this W1 matrix. Okay, for that sake we are taking W1 in terms of matrix, because we need to represent all these connections, correct? So every neuron is connected with this particular, see individually if I say x1 is connected with W2, x2 is connected with this, x3 is connected with this, then I don't need matrix over there. I simply need one vector. But here I am saying every neuron of this layer is connected with every neuron of this layer. So we need a matrix for those connections, dense connections. Okay. Right. Go through this. You all can note down this and try to solve it. Done? Okay, let me give you the options. Have you noted, all of you?
Yes, ma'am.
Okay. Note down these options as well. Done? And try to map now. Okay, have you got the answer? Is there any issue in understanding the problem? I just wanted to check whether you understood the terms like parameters with respect to number of parameters which are required to connect with layers. So that's why I framed this question.
Ma'am, please explain this again.
Okay. What we have is we do have number of parameters which are required. Total number of parameters which are required. Fine. And here the second column is indicating the parameters. We know only two types of parameters. One is weight, the other one is bias. Okay. And layers are L-1 layers are representing the hidden layers, and output layer is representing output layer, you know, the last the resultant layer, that is output layer. Okay. Someone asked what is K? K here is number of outputs. Okay. And you can think that we do have equal number of neurons in each of the layer. How many neurons we will be having? We will be having n neurons. Are you all trying to solve?
Excuse me, ma'am.
Yes.
Ma'am, what is this small l denoting actually?
Small?
Yes, ma'am. What does this small l denotes?
Okay, this is not L, this is 1, 1.
Okay,
1.
ma'am.
Okay, 1 into K into 1, and this is 1 into N into K. This is 1, okay, L-1. Again, this is L-1 layers. Here it is L layers including the output layer, but I am representing this as hidden layers. For that sake, L-1 layers. Okay, you try this. I hope you all have noted this question, correct? Let us try to solve these problems first. Later on, I will give enough time to solve the previous one. Okay, consider the neural network. Okay, before answering, you just let me know what is the input, how many input layers, how many input layers we can have in feed-forward neural network.
1.
Only one
1.
input layer is possible. How many output layers we can have?
1.
Ma'am, 1.
1. As I explained earlier also, we always have one input layer and one output layer. The only change that I can do with respect to number of layers are hidden layers. Okay. Now, try to solve this. Find the number of hidden layers in the above figure.
Ma'am, 4.
4? Yes. It should be C, that is 1, 2, 3 and 4. Correct? Next question. Try to solve this as well.
Ma'am, 3.
Okay. So which one is that? Find the number of neurons in the third hidden layer. We know this becomes the first layer, that is input layer. This is first hidden layer, second hidden layer, and third hidden layer. I asked number of neurons in this layers. Most of you have answered it correctly. That is 3. Right? Try to answer this.
3 cross 3. Option B.
It should be 3 cross 3. Correct? That is B option. Fine. Because we know that first hidden layer is this, second hidden layer is this, and these connections are representing my weight matrix. Right? For that sake, it should be 3 cross 3.
From 3 cross 1.
Okay, so it should be 3 cross 1. Correct. So now I have not represented the bias, but you all know if we don't represent also, we know that the dimension of the first bias which is possible is this. Okay, for the first bias. So it should be 3 cross 1. Okay.
From 2.
It should be 2. Okay, one layer, one input layer with 2. Yes, 2 inputs. Very much correct.
Ma'am, 1.
Yes, it is 1. Correct. Because we only have one output unit. Okay.
Ma'am 4.
It should be 4. Answer is already there. Okay. Try this.
5.
5.
Okay. So here again input layer. This is representing the output layer. This is first hidden layer, second hidden layer. So you all can count easily and have answered it correctly. It is 5. Okay.
D, ma'am, none of the above.
Okay.
I think 2 cross 3.
Okay. So let's wait for 2 more options from students.
2 cross 3, ma'am.
It is 2 cross 3.
2 cross 3.
2 cross 3.
Okay. So the answer is this 3 cross 2. Can anyone tell me why it should be 3 cross 2? Why not 2 cross 3?
मैम जो वो था ना हमारा फॉर्मूला, उसके अंदर WI XI था, XI WI नहीं था, तो अब हमें हमको यहाँ पर 3 नोड्स को तीन वेट्स लेने पड़ेंगे, तो इसलिए पहले हमको थ्री ऑर्डर लेना पड़ेगा, फिर उसको 3 cross 2 बनेगा, क्योंकि XI तो 2 ही है और नोड्स हमारी 3 है, तो 3 cross 2 ऑर्डर बनेगा.
Yes, yes. So here what we need to do is definitely we do have the weight matrix W is there, which what is the role of W is connect input layer, this input layer to this hidden layer. Okay, we know that there are only possible inputs are 2 and possible hidden neurons are 3. Fine. So according to that, it is 2 cross 3 matrix. It comes out to be 2 cross 3, as most of you have answered. But when we solve that, when we need to solve that linear function, as I explained in the presentation, so it was like summation of wi into xi plus b. So we all know that wi from your school days, we have seen wi, dimension of wi and xi. So we know that it should be mapped. When it is mapped, whenever C1 of first vector matched with R1 of the second vector, getting it? So whenever the columns of number of columns of the matrix mapped with number of rows of the vector, whenever it is matched, then only we can perform that multiplication operation. Correct? So for that sake, it should be taken W transpose X, that is 3 cross 2. And we all know what should be the dimensionality of this layer, input layer. It comes out to be, though I have not listed right now, but you all always answer it. What is the dimensionality of the input layer?
2 cross 1.
2 cross 1. So 3 cross 2 into 2 cross 1, it comes out to be the matrix multiplied by this particular given vector. So whenever we do multiply, then what is the result? We will get 3 cross 1 as the result. Okay, so that 3 cross 1, whatever result that we do get, that will be added with the first bias values, and it will produce what? It will produce 3 into 1 output. Okay. Okay, let's move to the next question.
Three cross 1.
3 cross 1. As we have solved while solving the previous third question, we have answered this as 3 cross 1, correct? This also has been answered while solving that. Yes, it is 2. It's very much easy to compute. Yes, it should be C. Fine. That's it. Let us move back to the first earlier question. I hope now everyone are familiar with those 2 sample examples. Now you should be able to map this.
Excuse me, ma'am.
Yes.
Ma'am, can you please solve an example for us? Because I'm not getting what we need to do here.
Okay. I just wanted to map the number of parameters, okay, with the weight and parameters and layers. Let us take the first one. Let me solve the first one for you. L minus 1, okay, number of hidden layers multiplied by n will give me total number of parameters. For what it will give me total number of parameters as L minus 1? Is it the weight matrix or is it the bias? We need to find that. You can tell me for what we will be having, forget about this L minus 1, because L minus 1 I have added only because I wanted to compute total number of parameters which are required for the entire network. Fine. But let us try to get first with the help of this dimensionality. This dimensionality represents whether it represents weight or bias with respect to hidden layers, because this itself is indicating hidden layers, right? It should be definitely with the, it should be mapped with bias. Can anyone tell why it should be mapped with bias?
For the purpose of addition, they should have same order.
Okay, because we have considered uniform, that means n number of neurons in each. Okay, and my bias, what it will do is the dimensionality of bias in with respect to for each of the hidden layers are will remain as n cross 1. Correct? L minus 1 into n cross 1. So it will remain same. So now 1 y will be mapped. Now it should be mapped with either L minus 1 layers or output layer. N number of, it is P, correct? L minus 1 layer, because we ourselves considered so many layers, L minus 1 number of layers in the parameters. Sorry, L minus 1 number of hidden layers. Okay, so 1, Y and P has been mapped by me. In a similar way, try to map these three. K is number of outputs. Try to solve the second one, L minus 1, N cross N. Because each of the neuron in each layer, we do have uniform number of neurons. So the weight matrix, we know dimensionality of the weight matrix should be N cross N. Okay, so L minus 1 for L minus 1, that means we are computing for, we are trying to compute for hidden layers. For each hidden layer has N cross N. What it will have N cross N? We all know it will not be biased, because N cross N itself is suggesting that it is a matrix. And we know weights are in the form of matrix, right? So 2 will be mapped with X, and because we ourselves have checked that for hidden layers. So 2x and p will be mapped. In a similar way, try to map this. We have one layer, k cross 1 neurons. When it is possible, 3, y and q. Okay, next, fourth one. Someone has answered. Fourth one is mapped. We know one layer is with respect to output layer, 1 into n into k. Okay, so that is mapped with k, n cross k, that is weight matrix, and weight matrix is further mapped with my output layer. So among these, the answers that we have computed today are, is, if I number them A, B, C, D, so our output is C. Correct? So these are the different references that I have referred for today's session. Sakshi?
Yes, ma'am.
Yes, I'm done with today's session. If any queries are there, then I can take. With respect to previous class or today's class.
Anyone
Excuse me,
have
ma'am.
doubt?
Ma'am, can you please show the slide number 10? Okay, ma'am. Thank you.
Anyone else?
Ma'am,
Yeah.
can you repeat slide number 9 again?
Slide number?
9.
Okay, this is there in the slide number 9.
Yes.
You want me to repeat?
Yes, ma'am.
Okay. So what we have, I just wanted to check your understanding with respect to feed-forward neural network architecture. For that sake, I have framed this question. So how many parameters are will be mapped with respect to weight and biases with respect to each of the layers? For example, L minus 1 number of layers, what we have, L minus 1 number of hidden layers have n cross 1, okay, n number of biases, okay. Similarly, L minus 1 hidden layers will have n cross n parameters with respect to weight matrix, okay. In a similar way, one layer, that is the output layer has k cross 1, okay, k cross 1. So k cross 1, we know that for if I say that if I need to map this k cross 1 with respect to weight, that is not possible, because we know that each matrix is has equal number of neurons, that are n, and only the last layer, that is output layer, has k number of neurons. Fine. So for that sake, what we can do is we can think that k cross 1 here will not be the weight matrix possible, which is not possible actually. So it will be bias parameter only, right? And we know that because why we are mapping further with output layer, why not hidden layer? Because we have taken it for output layer only. For that sake, there is a k cross 1 bias at the output layer. Fine. Think that output layer has 2 neurons and k here is 2. So what should be the dimensionality of the bias term? Bias term should be 2. Correct? 2 cross 1. One will be one bias term will be moved to or passed to first output neuron, and second bias term will be passed to second output neuron. In a similar way, the last one, that is, we do have n cross k. So when it is possible, because we do have n number of neurons in the last hidden layer, and I need to connect last hidden layer with the output layer, correct? So n number of neurons of the last layer will be connected with k number of neurons in the output layer. So that is only possible whenever we do have n cross k matrix, okay. So that is that will not be mapped with bias, it will be mapped definitely with weight. And definitely we are talking with respect to, or we are relating this with respect to last layer, hence it will be output layer only. Okay, I hope this time your doubt might
Got it, ma'am.
clear.
Thank you.
Any further doubts?
Anyone else having any other doubt?
Yeah. Just one question. Why is the output layer the first parameter, like in number 4?
Can you repeat your query, please?
Yes. Number 4 in the number of parameters, right? You have 1 cross n cross k, and the 1 represents the output. Why is the output the first parameter?
Can you send me through chart? I'm not able to get your query.
Okay.
Sakshi?
Yes, ma'am. I think it has written question in the chat window.
Okay, okay, okay. Very good.
He's asking about the first parameter. I think might be the weight.
Why is it the first parameter? He has linked previous source. Okay. 1 into n into k, 1 represents the output. Okay. Y is the first parameter. Oh, just for making you to understand, or indirectly, I wanted to know whether have you understood the terms weight and bias, and with respect to its dimensionality, input dimensionality and output dimensionality. Definitely, okay, students, don't we never use L minus 1 into n or 1 into k into 1. Here, I just wanted to make sure you have understood how do we map weight with respect to each layer. Okay, for that sake, I framed this question. And don't confuse with that I have placed 1 over here, but in fact it is the last layer. We are computing it for the last layer. Okay, I myself explained why before solving this question. I explained there are L minus 1 hidden layers and 1 layer at the output.
Okay.
This is not the standard representation. This column is not at all standard representation. I just wanted to make sure that you have understood the dimensionality of each of the layers. That's it.
Okay. Okay. Thank you very much.
Anyone else? Ma'am, I don't think there are more doubts now.
Okay, Sakshi. So we will close the session now.
Yes, ma'am. Thank you
Okay.
so much.
Thank you, Sakshi.
So I have pasted the attendance link in the chat window. Submit your attendance on time, everyone. And I think we are good to end the session for today then. Thank you.